Okay, it's preparing the transmission. Checking YouTube live.
Yeah, meeting is now streaming live on YouTube. Perfect.
Yeah,
Okay.
I think that we will start.
It's
Okay.
right in time.
Welcome to everybody to this semi-plenary session. It's a pleasure to introduce you Tomás Jungwirth. He's the head of the Department of Spintronics and Nanoelectronics in the Academy of Science of Czech Republic. And he's also a professor in the University of Nottingham in UK. He's expert in theoretical condensed matter in general, and the main topics of his research are related to magnetotransport, magneto-optical and electronic properties at the nanoscale, spintronic devices based on non-magnetic, ferromagnetic or antiferromagnetic materials, and anomalous and spin Hall effects, only as a few of his research topics. Today he will talk about antiferromagnetic spintronics, from memories to ultra-fast optics, neuromorphics, and topological phenomena. Please, Thomas.
Thank you, Agustina, very much for the introduction, and I would like to thank all the organizers of this conference to give me a chance to participate in this Zoom exercise online conference. So welcome everybody, good afternoon. So let me give you an overview of this emerging field of antiferromagnetic spintronics, which is becoming very broad, as also indicated by the title. And first of all, I have to acknowledge that this is really a very rapidly growing field, and there's no way that I can introduce all the key contributors to the field. So in this slide, I'm just trying to do so by showing you a few review articles that have been published in 2018. And here you can see at least some of the key people that have been contributing to the field. The problem with introducing all the people and the entire field is based in antiferromagnets themselves, because antiferromagnets are very abundant. They're much more abundant than ferromagnets. So intrinsically, once we start to play with antiferromagnets, start to build devices, the field can grow very rapidly. Antiferromagnets are very abundant, which also means that they can be insulating, they can be semiconducting, metallic, or even superconducting. And there's absolutely no chance that I can cover all these different types of antiferromagnets and devices in this talk. So in this slide, I'm just highlighting the part of the growing antiferromagnetic field, which I will not cover today, and that's on insulating antiferromagnets. There's been a lot of activity lately combining antiferromagnetism and insulating ferroelectrics, for example, looking at very fast spin dynamics and low damping spin transport by magnons in antiferromagnets, or even starting to build some antiferromagnetic electrical memory devices based on insulating antiferromagnets. But the focus of my talk today will be on conducting antiferromagnets and on spintronic devices that are based on these materials. It's conducting antiferromagnets. It makes it more similar to the traditional ferromagnetic spintronics, which is also largely based on conducting or on metallic systems. And again, just one example of a recent review article. So this is a recent review by the Illinois group on these metallic antiferromagnets and the devices. So as I mentioned, conducting antiferromagnets are from the conductivity perspective are more similar to typical materials used in ferromagnetic spintronics. And I will, when I go through the talk, I will make frequent comparisons to ferromagnetic spintronic devices. And the talk is divided into two basic parts. In the first part, I will talk about reading information that is recorded or stored in antiferromagnets. And in the second part, I will talk about means of writing information in antiferromagnetic spintronic devices. So let me start with readout. And as I said, I'm going to start by comparing antiferromagnets to the much more mature and commercially very successful field of ferromagnetic spintronics. So in ferromagnets, readout, electrical readout was first done by the so-called anisotropic Magneto resistance effect, where schematically it's shown on this view graph here, where when you change the direction of magnetization in a magnetic or ferromagnetic resistor, its resistance would change. It would depend on the relative angle of the magnetization and of the probing electrical current. Now the origin is relativistic spin-orbit coupling, and whenever we have relativistic spin-orbit coupling, typically the phenomena tend to be, or the effects tend to be relatively weak, and this is the case of the ferromagnetic and isotropic magnetic resistance, which is typically of the order of 1%. Well, despite the small effect, AMR was introduced as a means to read information on read heads of various magnetic media, but it actually was also the first readout mechanism in the solid state magnetic random access memories in the 80s. But of course, the real breakthrough in spintronics and also in spintronic devices was the discovery of giant and tunneling magnetoresistance, where now the difference is that we do not have only a single layer, a magnetic film on which we're trying to detect electrically the magnetization, but we have a system which contains a reference magnetic layer in which the magnetization doesn't change, and this sensor magnetic layer in which the magnetization changes, in this particular case, as it travels on top of the bits of a hard disk. And so we can have, in principle, two relative orientations of the recording or the sensing a magnet and the fixed reference magnet. They are either anti-parallel or they are parallel. And in case of parallel alignment, there's a large current going through such a stack, and when they are anti-parallel, there's a small current. So it basically acts as a magnetic switch of electrical current, makes it a very sensitive magnetic sensor. So this was a breakthrough technology that allows for the high density hard drives today, and it also allowed for their commercialization of the magnetic random access memories with this tunnel magnetoresistance readout. The effect does not rely on relativistic spin-orbit coupling. It relies on the non-relativistic Coulomb exchange interaction, and that allows it to be much larger, of the order of 100%. Now, in antiferromagnets, or we are talking about antiferromagnets today, there is no obvious generalization, or at least up to date, it has not been realized experimentally to have an analog of the giant or tunneling magnetoresistance in antiferromagnetic bilayers. There would not be an obvious difference when you would reverse one or the other Néel vector in this sensing or recording ferromagnetic film. So GMR, TMR has not been realized in antiferromagnets to date. So we will, throughout the talk, we will just rely on single layer, simple antiferromagnetic films and use those for reading and later on also for writing information. An example here is one of the workhorse metallic antiferromagnets, copper manganese arsenide, and here you see a transmission electron microscopy image of the single layer antiferromagnetic material. So we just rely on conductance of a simple film. So let's take a look from the symmetry perspective, what types of response is allowed in these magnetic systems. And if we just look at the conductivity of a simple film, we can split it in two parts. The first part is the symmetric conductivity or resistivity component, and the other one is the anti-symmetric component. And when we just combine this with the Onsager relations with respect to the time reversal or reversing the spins, we realize that the symmetric component is even on the time reversal, which also means that when we flip the moments, when we reverse the magnetic order, these symmetric components do not change. This is different from the Hall effect in this antisymmetric Hall components. When we do the time reversal operation or when we flip the spins or the moments, this Hall effect changes sign. So Hall effect is odd on the time reversal or on the spin reversal. And this implies that if we have systems which break time reversal symmetry, we can measure spontaneous Hall effect. Now, let's take a look at our antiferromagnets, and let's take a look at just a very simple model antiferromagnet as on this cartoon. When we do the time reversal, it means that we flip all the spins and we get into this middle state, and that is certainly different from the original one. However, we can then combine it with some trivial spatial symmetry operation like a half unit cell translation or this inversion around the center of symmetry here, and we would recover back the original state. So in effect, such a simple model antiferromagnet, linear antiferromagnet, has an effectively a time reversal symmetry, and that would disallow by symmetry a spontaneous Hall effect. So in antiferromagnets which fulfill this symmetry condition, and our copper manganese arsenide is an example of such a PT symmetric antiferromagnet, we cannot observe spontaneous Hall effect. Nevertheless, we still have the symmetric component of the conductivity, and it's this component in which we can measure the anisotropic magnetoresistance. So anisotropic magnetoresistance cannot distinguish 180-degree reversals of spin, but it can distinguish at different angles of the spin with respect to the probing current. And in principle, it's equally possible to observe anisotropic magnetoresistance in antiferromagnets as in ferromagnets. It's just that we would probe the change in the relative angle between the order vector in antiferromagnets, the Néel order, with respect to the probing current, and we will get two different resistance states. So this is an experimental realization of such an anisotropic magnetoresistance in our copper manganese arsenide when we reorient the Néel vector by 90 degrees. This anisotropic magnetoresistance effect does not exist only in the electronic transport, but it has counterparts also in optics, where instead of driving electrical current, we can shine a linearly polarized light. And now, depending on the relative angle between the light polarization and the Néel vector, we again have a larger or smaller light absorption. And so we can use this for optical detection, either in visible light, or we can also use X-rays, which also provide us with a high spatial resolution because we can have a small spot size with X-rays if we go to synchrotron. And so what you see here is a counterpart X-ray magnetic linear diaphragm detection of the 90-degree switching that we see before in electrical signal. Now we see it in the X-ray magnetic linear diaphragm signal, where we see this light domain corresponding one Néel vector angle switching into the dark domain, which corresponds to the orthogonal Néel vector angle. So we have a means how to detect it electrically. We also can go to synchrotron, and we can do a detailed microscopy of the switching. But going always to synchrotron is not very practical. It would be very nice to have some laboratory tool where we can do the domain imaging in antiferromagnets as well. And here we can take advantage of another counterpart of the anisotropic magnetoresistance now in the thermal phenomena. It's the thermoelectric Magnetosedec effect. So again, it's a counterpart to the anisotropic magnetoresistance, but here in this case, we do not apply electric current or electric field. Instead, we apply a thermal gradient, and now as a function of the angle between the thermal gradient and the Néel vector, we can generate smaller or larger electrical voltage in this thermoelectric effect. So we can use this also in a microscopy setup with a far field lower resolution or near field high resolution laser setup, where we scan the sample with the laser, create the thermal gradient, and then detect electrical thermal voltage across the sample, and by this we can image the domains. And here you see side-by-side images of the very same sample scanned by the synchrotron X-ray magnetic linear diachroism and by this laboratory thermoelectric magneto imaging. So we can do in laboratory not only electrical detection, but we can also do microscopy on our antiferromagnetic domains. So all these effects, the electrical, optical, and thermoelectric, were just direct counterparts of the same type of phenomena in ferromagnets. So now the question is whether we can do in our antiferromagnets also something that within that type of physics that would go beyond the possibilities of ferromagnets. And here, one theoretical proposal, which is yet to be experimentally verified, is a proposal for generating very large anisotropic magnetoresistance effect or their optical or thermoelectric counterparts. These are relativistic effects, and we already hinted that if they are relativistic, typically the effects would be weak. So how can we possibly enhance the magnitude of the effects? And here in antiferromagnets, we realize that because of this combined space and time revolving symmetry of our system, we have Kramer's spin degeneracy of our band. So if I look at the electronic structure or Fermi surface of our antiferromagnetic copper manganese arsenide, it is spin degenerate. So I have a spin up and spin down degeneracy of the band. This is similar to graphene or any other non-magnetic system where we have not a combined PT symmetry, but we have individual space and time reversal symmetry, and they also guarantee the Kramer's degeneracy. And also, in analogy to graphene, where we have two carbon atoms in the unit cell, they would generate two bands, and now I can have these two doubly degenerate bands which cross, and in the middle, in this crossing, I will get four full degenerate Dirac point. So this is a topological feature, which is a result of the PT symmetry plus having these two sites per unit cell. In our antiferromagnet here, we also have two manganese sites in the unit cell. So we also have these crossings of two doubly degenerate band, and we can also generate, because of the PT symmetry, this Dirac point. So this is something that does not exist in ferromagnets. In ferromagnets, we would always have splitting of this because the PT symmetry cannot be realized in a ferromagnet. So from that perspective, our antiferromagnet looks identical to a non-magnetic paramagnetic system like graphene, for example. But in graphene, we cannot further manipulate this Dirac point. This is not the case of antiferromagnet. In antiferromagnet, what we can see here is that this crossing, this Dirac crossing, is protected from hybridization only if our moments are pointing in some very high symmetry direction. But when we rotate the moments, due to spin orbit coupling, we break this symmetry that protects the Dirac crossing and we open a gap. So we can close and open the Dirac point gap just by reorienting the antiferromagnetic moments in our crystal. And if we can create a material, and one theoretical proposal is of rhombic phase of copper manganese arsenide, then this Dirac point sits exactly at the Fermi level, and there are no other bands crossing the Fermi level. So we have a Dirac semi-metal. And for one orientation of moments, the system is metallic, the back gap is closed, but for other orientation, we open a gap and the system becomes insulating. So we have a topological metal insulated transition generated by reorienting the antiferromagnetic moments. So in a sense, this generates an isotropic magnetoresistance where we change the system from insulating to metallic. So in principle, in antiferromagnets, we can have huge anisotropic magnetoresistance, which cannot be achieved by symmetry in ferromagnets. Now, let me move back to the antisymmetric component of conductivity, the spontaneous Hall effect. We discarded it in antiferromagnets previously, but maybe we were too quick. Maybe there are other realizations of antiferromagnets in which the symmetry, even the effective PT space-time reversal symmetry, will be broken and spontaneous Hall effect will be allowed. This is indeed the case. It has been realized several years ago that if you make a more complex antiferromagnetic state, where still there is a vanishing net moment, but we have now 3 sublattices of non-collinear moments. They all together compensate into 0 net moment. However, there is no time reversal symmetry in the lattice. There is even no time reversal combined with some simple translation or inversion. It does break all the necessary symmetries for the spontaneous Hall effect. And soon after the theory prediction, indeed, a large spontaneous Hall effect was observed in this non-collinear antiferromagnets. Example is manganese 3 tin. Now, to ultimately observe the anomalous Hall effect, you also require this relativistic spin-orbit coupling. And again, that means that the magnitude of the anomalous Hall effect as another Magneto transport phenomenon in a single layer magnetic film is relatively weak, of the order of a few %, similar to AMR. And that applies equally to ferromagnets and these non-collinear antiferromagnets. You can also observe all the counterparts, either optical, X-ray, or thermoelectric, to the spontaneous Hall effect. And here is an example of a measurement of the thermoelectric imaging of the domains in these non-collinear antiferromagnets using this thermoelectric anomalous Nernst effect. But now the question is whether we really have to go to this more complex non-collinear antiferromagnets to observe spontaneous Hall effect and all the other counterparts. The question is important because these materials are quite rare. There are not many non-collinear antiferromagnetic materials that we can explore and exploit. There is many more of collinear antiferromagnets. So the question is whether really it is by symmetry completely excluded to have spontaneous Hall effect. Now the answer to this is no. In fact, it's quite easy to generate spontaneous Hall effect also in collinear antiferromagnets, and even in the ones which have just the 2 opposite spin sublattices. The only thing we have to do is to break this PT symmetry, and the way to do it is to introduce in the lattice additional non-magnetic atom, like here, which is shifted from this original center of symmetry point. So now it's a non-magnetic atom in the lattice, which actually guarantees that the crystal breaks the PT symmetry and all other symmetries required for the spontaneous Hall effect. So this is it's been a very recent proposal, theoretical proposal, which also subsequently has been verified experimentally in such a collinear antiferromagnet. Now, the specific example is ruthenium dioxide, and it is an example of a very common family of rutile materials or rutile antiferromagnets, which have been extensively studied and known for many decades. In fact, already Nail, in his seminal works, was talking about rutile antiferromagnets. So these are very common materials. Now, let me take a little closer look at what's really happening in these materials once we introduce this non-magnetic atom in the lattice. So we said that with just the 2 magnetic atoms with the opposite moments, we would not generate the anomalous Hall effect. The system has a symmetry which is too high. But once we introduce this non-magnetic atom and we put it in this non-central symmetric positions, what you see is that the magnetization densities of these 2 magnetic atoms become highly asymmetric or anisotropic. So then by just looking at these magnetization densities and their anisotropy, you see that the system breaks all the symmetries. You cannot do just the spin reversal and shift it, translate it, or do the inversion and to recover the same state. It's this asymmetry in the magnetization density, which is generated by these non-magnetic atoms, that breaks all the necessary symmetries. But this, in principle, is a non-relativistic effect. To observe the Hall effect, to observe the electrical signal in your Hall measurement, you need to still have relativistic spin-orbit coupling. But to generate these asymmetric magnetization density, That already happens without relativistic spin-orbit coupling. It's just a consequence of Coulomb interactions in the crystal. And so what we observed as a correspondence is a new topology of the Fermi surface or of the electronic structure, even without spin-orbit coupling. The fact that we now broke the PT symmetry means that we broke the degeneracy between spin-up and spin-down state, but we did it while still preserving zero net moment in the system. So the splitting of the bands is something that has no counterpart in the earlier explored spin splittings, either in ferromagnetic systems or in the non-magnetic relativistic spin-orbit coupled systems. What we have here are two bands where spin is a good quantum number. So we have a spin-up and spin-down bands, but they are distorted and split apart by this anisotropic distortion here. While in ferromagnets, when we generate the splitting, we just reduce the size of one band at the expense of the size of the, let's say, the minority band at the expense of the size of the majority band. While in this broken space inversion symmetry non-magnetic relativistic system, we generate a spin texture where on one side we have, let's say, spin downs, and on the other side we have spin ups here. But in the spin texture, spin is not a good quantum number. So one of the direct consequences of such a new type of topology of Fermi surfaces is a generation of a very strong spin current in these systems, which is purely of non-relativistic origin. So you can understand the presence of this strong spin current in a way that electrons, let's say the spin down electrons here in this anisotropic band, they would have a much higher conductivity, let's say along this direction than along the orthogonal direction. So now when I would apply electrical current at an intermediate angle here, then my electrons, as they flow through the material, they would tend to bend towards the higher conductivity direction. So in the real space, my spin down electron, which moves primarily in this spin down sublattices, when I apply electrical current, it would deflect in one direction. On the other hand, the spin up electron has the anisotropy rotated by precisely 90 degrees, so it would deflect in the opposite direction. And this is of a non-relativistic origin. It's purely Coulomb, and the effect can be very strong. This conversion between the charge current into the spin current can be as large as 30%. So this was just an illustration what new type of topology that does not exist in ferromagnets and does not exist in relativistic spin-orbit coupled system can give us in antiferromagnets. But a generation of spin currents is something that is more already in the direction of writing information in devices rather than readout, because typically in spintronic devices, we write or we switch the magnet by generating spin polarized currents. So this for me is a natural way how to proceed to the second part of my talk, in which I will now focus on the writing. And again, I will start by making a comparison to the conventional ferromagnetic recording and ferromagnetic spintronics. So recording started not with electrical currents, but as we still know it in hard drives, you can record or you can switch ferromagnet by applying external uniform magnetic field, as done here by this coil on a ferromagnetic hard drive. Now, if you would like to replicate the same method for magnetic recording in antiferromagnets, you would have to wind a coil individually around each magnetic atom in a way that one coil would generate magnetic field in one direction and the neighboring coil in the opposite direction. So this was presumably one of the reasons why Neil considered antiferromagnets interesting, but in practice useless, because nobody can fabricate such a device with billions of coils wound around each individual atoms. But fortunately, we don't live now in the era of magnetic recording. We live in the era of spintronics. And in spintronics, we use spin polarized electrical currents instead of magnetic fields to write the information. So one way how to do this, a very natural way in ferromagnetic spintronics, is to use the same structure that is used for readout, for the tunneling or giant magnetoresistance readout, where we have the reference and the recording magnetic layer. And now instead of sending a low probing current, we send a high writing current. So we send many spin polarized electrons from the reference magnet into the recording magnet. And if we can transfer enough angular momentum from the reference to the recording ferromagnet, we can generate switching by electrical means. So this switching is based on the ferromagnetic spin splitting of the bands, which can allow us to generate these highly spin polarized electrical currents. This method is now used in the commercial spin transfer torque MRAMs, but there is another method which is now under the development in prototype devices. And it's a method which is trying to circumvent one of the problems here with the spin transfer torque, which is the fact that the writing current has to be driven through this insulating barrier in the tunneling device here. And if we have to drive strong writing currents through a very thin insulating barrier, we can cause damage of the device. So it would be more favorable to run the writing electrical current laterally in the ohmic part of the device. So how can we do this? So first, we need to think of a non-magnetic system. For example, like this paramagnetic system with spin orbit coupling and broken space inversion symmetry. And what you see and what we already mentioned is that on one side, let's say left movers have spin down and the right movers have spin up in equilibrium. So now when we generate electrical current, we will have an excess of spin up electrons in the system. So a non-magnetic system, which is relativistic and breaks inversion symmetry, under applied electrical current can generate uniform non-equilibrium spin polarization. So now the final step is to combine this effect with a ferromagnet, or combine this effect at an interface within ferromagnet, and then this non-equilibrium current-induced spin polarization can again switch the recording ferromagnetic field. The phenomenon is known under the name spin orbit torque because it's relativistic in origin. And again, it can be used for reversible switching by changing the current polarity. And as I said, this phenomenon is already in the stage of research and development in many labs and companies towards embedded magnetic random access memories for computers and for embedded also in processors. So it's a very efficient method, can be very fast in ferromagnets. So the question is whether we can learn some lesson from these ferromagnetic spin orbit torques and from these relativistic current-induced spin polarization effects to switch also an antiferromagnet electrically. And we will take our workhorse antiferromagnet, copper manganese arsenide again. Now, we already seen that this is the simple antiferromagnet, which has this PT symmetry. So we have spin degenerate bands. So it's quite tricky to think that in such a system, we can generate spin polarized currents and use those to switch the antiferromagnet. Nevertheless, we can do this. And the reason for this is that, yes, the bands are spin degenerate, but we still have relativistic spin orbit coupling in the system. And yes, the system, the lattice, has this inversion symmetry point, the non-magnetic lattice has this inversion symmetry point, which means that running electrical current cannot generate a uniform net spin polarization. However, locally, the individual sites in the lattice are not centers of symmetry. In particular, the sites occupied by the manganese atoms here, these are inversion partners, meaning that this is not a center of symmetry. This is also not a center of symmetry. They have a locally broken inversion symmetry environment, but they have it broken in an exactly opposite way. So combining relativity with this local inversion asymmetry, what can happen is that when we run electrical current in such a lattice, we do not generate a net spin polarization, but we generate local spin polarization of carriers, which points in one direction around one of the lattice sites and in the opposite direction around these inversion partner lattice sites. And because these inversion partner sites are occupied by opposite antiferromagnetic spin sublattices of the antiferromagnet copper manganese arsenide, we have commensurate staggered current induced field with the antiferromagnetic staggered order. So the two couple strongly, and we can use this electrical effect to switch the antiferromagnet. And this is the mechanism which we now ascribe to the observed 90-degree switching that I've already mentioned earlier in the talk when talking about readout in copper manganese arsenide. We can control this switching between the light and dark domains, between the two nail vector directions with 90-degree angle with respect to each other. We can do this by reversing the current that we apply through the crystal. And we can do this reversibly and reproducibly. See this in the microscopy and also see this in the anisotropic magneto resistance signal. So now we have all necessary tools for building a memory device. We have electrical readout through anisotropic magneto resistance. We have writing through the antiferromagnetic spin orbit torque. So we decided just for a demonstration to build a prototype device in which we embedded one of our devices on a digital printed circuit board, connected it to the computer, and show that in ambient conditions we can write and read zeros and ones in such a device. So I can make a quick summary of the observations that we made so far when talking about reading and writing information in antiferromagnets. We adopted principles which were analogous to the reorientation switching known from ferromagnetic spintronics. And we've done this in single layer antiferromagnetic films. And while we were able to successfully demonstrate all these functionalities, even all the way to a demonstrator toy printed circuit board device, we inherit all the limitations or the weaknesses of this reorientation switching principle if adopted in single layer magnetic films. So one of the problems was that we mentioned already is that in these single layer films, we tend to rely on relativistic effects like anisotropic magneto resistance or anomalous Hall effect, and those give us low readout signals, and low readout signals would limit the functionality of the devices. And another common problem, which is not only related to single layer films, but to just the current induced spin torque principles, whether in single layer films or multi-layers, is that there is no direct extension of this principle into optics. And eventually, if you want to achieve very fast switching, we need to go from delivering electrical pulses into delivering optical pulses. So with the principles of current induced spin torques, we have no means how to connect the two worlds of electrical and optical spintronics. So in the remaining several minutes, let me just introduce to you a new switching mechanism that we discovered in antiferromagnets, and we believe is again requires an antiferromagnetic stray field system, because to the best of our knowledge, this type of switching has not been reported earlier in ferromagnetic systems. We call the switching a quench switching into a nano-fragmented domain states. So let me just do a side-by-side comparison between this new type of switching with the traditional reorientation type of switching. So when reorienting the large domains, as I showed you in the movies several times already, We do it in our copper manganese arsenide. We start from a phase in which we have these large domains where the dark is one nail vector direction and the light domain is the orthogonal one. And we can switch between light and dark by delivering these electrical pulses. The pulse amplitudes are in the 10 to 6 amps per centimeter square, which is the typical current amplitudes also used in the counterpart ferromagnetic devices. Now, remarkably, if we take the very same device, the very same material, and we only increase the switching current by a little bit into the 10 to 7 range, instead of having these reversible switching of the black and white domains, what happens is that we shatter the domains into these nanofragmented state. We call it quenching because it cannot be done by slow pulsing or by pulsing by very long DC excitations. We need to deliver at least milliseconds, but the shorter the pulse, the better. So we need to quickly excite the system and then quickly quench it into this metastable frozen state with many nanofragmented domains. So we can image this, switching by, again, the synchrotron microscopy, but we have also alternative laboratory tools in which we observe this quench nanofragmentation switching. One was using the nitrogen vacancy diamond magnetometry, and the other one was, again, the effect that I already introduced earlier, which is the Magnetosedec effect.
5 minutes.
Thank you. The advantage of using the laboratory tools is that we can do much more systematic study than using just beam time at synchrotron. So we can observe at a much, for example, longer time scales what happens with our switch states. And here what we see is that this nanofragmented state is really metastable. It tends to relax towards the large domain state here. So when I now show you the electrical readout counterpart of these microscopies, this is how the signal looks like. We deliver a pulse. Now we can either deliver an electrical pulse or we can deliver equally well optical pulse. And what happens is that we switch the state into a high resistive nanofragmented domain state. And we observe some relaxation, which from the microscopy, we interpret that the state relaxes towards a larger domain state. But what is remarkable in terms of switching is that we can now deliver another pulse, and a pulse which is a lower amplitude can be in the same direction. So polarity doesn't matter, or polarization of light doesn't matter, but it's just the amplitude. And if the amplitude is lower, we can quench the state in a lower resistance state. So the resistivity state towards which we switch the system does not depend now on the direction or polarization of the current, but it depends just on the amplitude of the pulse. What is also remarkable is that the switching patterns in these devices can be absolutely 100% reproducible. And also what we found intriguing is that the size of the switching signal can approach 100%. So we can get changes in the resistivity, which are of the order of residual resistivity of our film. We don't have to introduce any multi-layer, complex multi-layer stacks like in the ferromagnetic tunnel magnetoresistance or GMR effect. We can still rely on a single layer film, and yet we achieve these 100% resistive switching. And as I said, we can use electrical pulses, nanosecond pulses. We can even use terahertz field, ultra short picosecond pulses, or go to infrared lasers and hit it with a single 100 femtosecond optical pulse and also achieve the same type of switching. And again, controlled by the amplitude or the intensity in this case of the laser. Now, the 100 femtosecond pulse was the shortest that was available in our lab, and we still observe the switching. So we don't really know what is the limit in terms of the pulse length, but it can be well below this 100 femtoseconds. So this was the phenomenology of this quench switching in terms of the switching signal. What is equally intriguing to us is also the retention or relaxation characteristics, if you want. As I said, we are switching now not into a stable equilibrium state, but into a metastable quench state here. So we see this, this relaxation, but also the relaxation pattern is absolutely reproducible. So now we can think of building, instead of digital devices, we can start thinking of analog devices, for example, for analog neuron-like networks, where we know that we need to realize two basic functionalities. One is to somehow detect the order and delay between pulses, which is the functionality which is used to set up the synaptic strength, or to have a functionality of the leaky sum of pulses, which is the functionality of the neuron potential. And we see that in our devices, we can perfectly distinguish the order and also the delay between pulses. We see that if we deliver the weaker pulse second, we have a falling edge. If we deliver a stronger pulse as a second pulse, we have a rising edge here. And now the delay between pulses is coded in the size of this falling edge. If the delay between pulses is long, then the falling edge is small. If the delay between pulses is short, we have a large falling edge here. And also, if we deliver a sequence of equal strength pulses, we see that we keep on steadily increasing the signal on our device, including this leakage. So now it depends on the delay between pulses by how much our signal increases with each individual pulse, which is exactly the leaky sum functionality. Let me conclude the presentation by just a demonstration. You can just consider this as a toy proof of concept demonstration, where again, we're trying to see if we can realize all these functionalities, not only in our complicated laboratory equipment, but pack it all into a simple board. But now it's not a digital board controlled by a microcontroller or microprocessor. It's just an analog, fully analog board with just discrete components and our antiferromagnetic device. But we see that we can replicate exactly the same behavior also in this very simple board. So in the final demonstration here on my final slide, I will just show you an example where we put this board into our Internet of Things testing site, where we have a vehicle detection system, and our car just hits a sensor which sends a pulse to our digital board, and we have the first signal, then it hits a second sensor which sends a weaker pulse, and we have a falling edge. And falling edge on our board immediately is translated into one direction of the motion of car. Now, if the vehicle first hits the second sensor which sends a weaker pulse, and then the first sensor with a stronger pulse, we have a rising edge, and we know that the car arrives. So we have a very low power analog board with just a simple discrete elements without any microcontrollers or microprocessors, which can do this, if you will, very simple neuromorphic function on this edge IoT site. So with this demonstration of the possibility to think of not only about the physics and fundamental physics of antiferromagnetic spintronics, but maybe also of some future non-conventional neuromorphic applications. Let me thank you all for being here, for listening, and let me also thank all the funders and our sponsors, both from the public and private sectors. Thanks a lot.
Thank you very much, Thomas. And I appreciate the nice movement from the very fundamental concepts to this prototype. It's very, very nice. Well, now it's time for questions. We have already some of them. Lucia Valle asked, does the current threshold for quenching switching shift with base temperature? You mentioned reproducibility of the domain landscape regarding sizes or actual position of domain and walls. And thanks.
Thank you very much for the question. So the first question was whether the threshold current depends on the base temperature. Our observation is that to achieve the quench switching of a certain signal, it appears that we need to deliver a certain amount of energy into the system. or for the very short pulses when all the energy is basically all the energy during the pulse is just absorbed by the device or by the film. If we had much longer pulses, then we would dissipate the energy also in the substrate, and then we would need a much higher energy. But when I talk about short pulses, meaning from 10 nanoseconds down, when during the pulse we do not dissipate the energy from the layer, then what we observed is that we just need to deliver a certain amount of energy to achieve a certain signal. And that would also correspond to heating the system to a similar temperature. So if I would change the base temperature, for example, if I would cool the sample, I would need to deliver a higher amplitude pulse to compensate for the lower base temperature in order to achieve the same, let's say, switching conditions. So from our measurements, for lower base temperatures, we would need to increase the switching current density or the laser power to achieve the same switching signal. In terms of the reproducibility of the signal, we do not have a very systematic and detailed microscopy of what's going on with the domains. But from the measurements that we have, we see that we have parts of the films which would really show the same type of switching of the same nano or micro domains parts. But we can also see some random switching events while the electrical signal, the average electrical signal, is still highly reproducible. So the high reproducibility could be partly because really on the nanoscale we switch the same object, but it also could be because of the fact that we have a micron-sized device, while our fragmentation is below 10 nanometer scale. So we basically average out even if the switching is happening at random places.
Next question is by Ignacy Fina. He thanks for the clear talk. He mentioned that in the coin switching experiment, what is the contribution of the domain walls between antiferromagnetic domains? He mentioned that if it is relevant or it cancels out. Do you think that you can make it relevant on purpose?
Hi, Ignacy. Thanks for coming to the talk and thanks for the question. It's a very good question about the domain walls, because what we see from the microscopies is that the scale of fragmentation is approaching 10 nanometers, even below 10 nanometer scale. We can only infer this sort of by extrapolation because the resolution of these microscopies that we use is of the order of tens of nanometers. But we can infer from the signal then the fragmentation has to be below that, below the resolution of our techniques. So we have objects which are 10 nanometers or maybe even smaller, while we simultaneously know that in the large domain state, the domain walls themselves have a size of many tens of nanometers approaching 100 nanometers. So in the state, which is an equilibrium state, if we have a domain wall, it would be the standard micromagnetic domain wall whose width is a combination of exchange and anisotropy fields, we would get a feature size of tens or maybe 100 nanometers. But suddenly with this coin switching mechanism, we are creating textures which are much smaller than the equilibrium domain wall sizes. So it means that we must be creating domains separated by domain walls which are much narrower than the equilibrium domain walls, which are sub 10 nanometers scale. And we have now, and this is a preliminary work, unpublished work, where we start to see first indications that indeed there are new objects in these antiferromagnets which cannot be explained by the micromagnetic theory, very abrupt changes in the magnetic order, which can be in the sub 10 nanometer scale. And we think that they will provide a clue of the nature of this nanofragmented state. But I am not in a position to say more about this because this is still work on the progress and things needs to be very carefully checked.
Next question is by Javier del Valle. What is the origin of this change of resistance when you quench your films? Very similar results are observed in phase change materials. Could you have partial amorphization?
We have several, I can have several answers to this question. None of this is a definitive answer because we don't have the definitive understanding of this mechanism. But let me say one at a time. So one example is that there is a theoretical work, a theoretical ab initio calculations that is comparing the conductivity of copper manganese arsenide of the very same material in the fully antiferromagnetic single domain state, and then in a state when the moments are completely disordered, are frozen and disordered. In those calculations, they were just mimicking a paramagnetic phase. But what it can also be is just the limit of having introduced an atomic scale disorder in the system. And what they observed is that the conductivity increases by several hundreds of %. So this just tells you that by freezing a strong magnetic disorder in the system can indeed increase significantly the resistivity. We don't think that we are necessarily creating a frozen, completely disordered state. We still think that it's more a state of domains separated by very sharp, very abrupt domains. We have some indications that this is a more plausible scenario, in which case I would attribute the increase in resistivity in the large domain wall resistance associated with these very sharp domain walls. So something like having a maze of small tunneling or giant magnetoresistance elements in our film, which are not generated lithographically or by growth, but spontaneously by the quenching mechanism. Now, in terms of comparison to phase change memories or resistive RAM memories, any types of memories where you change a structure, I can only say that we did very systematic study of the structure of these systems under the pulsing. And while we could identify a clear change in the magnetic signal, we could not identify any counterpart change in any structural, whether it's a crystal structure or a defect structure upon the same pulsing conditions that we use in these experiments. So we see clear signals in clear magnetic signals, but all our structural analysis shows that this is not a phase change or some resistive RAM type of memory.
Okay. Abdul Hassan asks if was there any aging effects in case of multi-level analog switching?
No. We've done, for example, with these optical experiments, we've done hundreds of thousands of switchings because we can deliver femtosecond pulses with megahertz repetition. And so we've tested literally millions of pulses, and we did not see any sign of aging of these devices.
Okay, more questions? There isn't a relationship between the temperature and these levels. I mean, you can change or control with temperature.
Whether we can control the temperature, the relaxation, was that a question?
Yes.
Yeah, exactly. So it's also interesting that this the relaxation, we studied in detail the functional form of this relaxation, and the form that we observe is very universal, and it's the so-called Kohlrausch stretched exponential. So it's not a simple exponential relaxation, it's a stretched exponential, meaning that first the relaxation is faster and then it slows down. So it has an exponential form with an exponent which is smaller than 1, and in the Kohlrausch theory it corresponds to basically a diffusion process in 3 dimensions, which also to some extent confirms that the objects that we have are very small because we have a 50 nanometer film. That means that the object's size must be much smaller than 50 nanometers to still have some sort of a 3D type of relaxation or diffusion process. So it's very universal. It's a stretched exponential, and Now, the relaxation time, the characteristic relaxation time as a function of temperature is exponential, is a simple exponential, as known also from this Kollarov's theory. And that means that it has a strong temperature dependence, which is again universal. And what is remarkable that we see in this view graph, I've only shown you one, let's say, part of the relaxation. This is the slow relaxation. But we also see a much faster, about 3 orders of magnitude faster relaxing component in the very same device, in the very same switching events. So if you want, you can operate this device in seconds or minutes timescales, but you can also operate the device in millisecond timescales simultaneously, because it has these 2 timescales that operate simultaneously.
Well, I think that we don't have more questions, especially we have to move because now we have the special sessions of the afternoon. Then thanks again. I will clap for everyone, and I don't know if you want to take a picture, perhaps the host of the session, Ramon. Well,
The host is Lola, but I mean,
okay.
What we have done in other sessions is to ask everybody to open their cameras and go to gallery view.
Yeah, but Thomas needs to stop sharing the screen.
Yes.
Yeah, sure. He stops sharing, and then everybody takes a screenshot. So we have many pictures. Each of us does the same in gallery view.
Okay.
Okay.
Okay. 1, 2, 3. Then the next window. 1, 2, 3.
Nice to see the faces finally. Thanks a lot for coming.
Thank you to everybody. Bye-bye.
Thank you, Thomas, for the nice talk.
Thanks for everything.
My pleasure.
Very good organization, so thanks a lot.
I will close the meeting, so maybe I will kick everybody out.
Okay, bye-bye. Thanks a lot again for organizing.
No problem. Like this, we have time for coffee before the special sessions.
Bye.
Bye. Thanks.